So I think we can start with the last talk of the workshop. So we are very happy. Raffaele will tell us about. I think it's like perfect talk for the type of workshop that we've been having, cosmology and particle physics. So please go ahead.
So thank you very much again for the invitation. So today we'll tell you about a new idea to explain at the same time the hierarchy between the weak scale and the Planck scale, and why the theta angle in QCD is so much smaller than we naively expect. And it will be based on these ideas of cosmological selection that have been starting to pop up lately. So I will start with a lightning introduction, although I'm sure that most of you know what I'm about to say. But so if you look at these two parameters, they don't seem to have much in common. So the theta angle of QCD is most sensitively measured through the neutron electric dipole moment, and generically is associated to strong interactions. While the Higgs boson mass squared, it's the second most relevant parameter in the standard model Lagrangian, and is associated to a field that is coupled only to electroweak interactions. And the value of mh squared is, in some sense, much more central to our description of nature than that of theta. Being so relevant, it means in a precise sense that it's very important at low energy, and indeed it determines the range of the weak force, the mass of most known particles, and through those masses also the existence of complex nuclei, chemistry, and at the end, life as we know it. So if you just look at this slide, you might think that these two objects have nothing to do with each other, different dimensions, different interactions, completely different role in our description of nature. However, well, they have in common one thing, which is that they are not calculable in the standard model. This is a much, let's say, milder problem for theta, which is only logarithmically sensitive to UV scales and only at 7 loops, but still, technically, they are both non-calculable. However, we might try to estimate them using symmetry. And of course, any such estimate implicitly means that we're making an assumption on physics in the UV. But if we make the simplest assumption and imagine that there is not a lot of extra symmetry structure beyond the standard model in this theory, then we're going to get these two results. So something of order 1 for theta, and if you are surprised, I can be more precise if you ask. And something of order of the largest mass scale in the theory for the Higgs mass squared. Actually, okay, if you combine different symmetries, you can be more precise. So space-time dilations tell you that you should go like the largest mass scale, and then another symmetry of free scalars tells you that you should go like the largest coupling. And then if you restore units to h slash, you can even predict the 16 pi squared. So this is all you see in this slide is purely based on symmetry.
So this one clearly is not the 7 loop.
No, this one, exactly. So as I was saying, I'm implicitly assuming that whatever is extending the standard model is not more CP symmetric than the standard model. So if you extend it very generically without adding structure, then you're going to find extra sources of CP violation that then feed back at order 1 into theta. So this is what this estimate really means. And these two estimates both differ from experiments by many orders of magnitude. So about 34 for the Higgs and 10 for theta. Of course, this doesn't mean that the standard model is inconsistent. It only means that the UV theory is not as trivial as those symmetry estimates imply. So these two parameters are telling us something about physics at high energy, and we would like to understand as much as possible about this physics at high energy. Next, so I'm gonna tell you about a known property of the standard model that relates these two parameters. So far, we've seen that they don't have much in common except for this puzzle related to their estimate versus their experimental determination. And this property has been known for a long time. You probably are all familiar with it. But as far as I know, this one that I'm gonna tell you about is the first joint explanation for the two parameters that leverages this idea. Actually, I think, well, as far as I know, this is the only joint explanation, period. Okay, so how did we get to thinking that this quantity in the standard model that relates the two parameters is important? So we got to there by asking a different question. So we started from wanted to explain just the value of the Higgs boson mass. And then, so we just asked this general question. So what happens to the standard model if you change the Higgs mass squared, or if you prefer the Higgs vacuum expectation value? And it turns out that, so essentially every non-local quantity that you can compute depends on the Higgs web. And this is not surprising because any on-shell endpoint function, so decay rate or cross-section or scattering amplitude for a massive particle will change if you change the Higgs boson mass. But interestingly, it turns out that there is only one local operator that depends on the Higgs web. And this operator is the asymmetric contraction of two gluon field strengths. So precisely the operator that is traditionally associated to the strong CP problem and the theta parameter. It turns out that there are a few solutions of the hierarchy problem, so for the Higgs mass, that make use of these on-shell quantities, but in practice, it's very hard to build a model that leverages this property of the standard model. And indeed, so as far as I know, there are only 3 explanations for the Higgs boson mass that use on-shell quantities, and probably the best known of them is the traditional anthropic argument. Okay, so the anthropic argument for the value of the Higgs boson mass essentially is based on 2-point functions in the standard model, so the masses of quarks. But what we're going to focus on today is this object here. So if you look at its vacuum expectation value, it depends on the Higgs web, both through the quark masses linearly, so the light quark masses up and down, and also through the QCD scale because of the running. So as you integrate out the quarks going down in energy, you're going to change the beta function, and so the QCD scale that here I represented as the K constant of the pion cube depends on the Higgs web. And interestingly, okay, this quantity also depends on the theta angle. And probably many of you knew this already. It's probably been known for about 50 years. But I think that this fact that the only local object that depends on the Higgs web depends also on theta has been a bit underestimated. I don't know, maybe you can tell me that I'm wading too much into it, but I think that it's extremely interesting that this is the case, especially because it's a total coincidence. So you need 3 coincidences in the standard model for this to be true, and no one of these coincidences is useful for anything else. And so, well, I'm starting to think, again, as a purely personal bias, that the standard model is trying to tell us something here. Because for this quantity to depend on the Higgs web, you need 3 conditions to be true, and if any one of them is not, then that would not be the case. So first of all, you need a breaking of this anomalous V1A symmetry in the standard model that can interfere with the breaking from non-perturbative QCD effects. So you don't need just any breaking, but something that can interfere and close all the instanton legs. Secondly, well, you need somewhere sensitivity to the Higgs mass squared, either in this explicit Q1A breaking, so the quark masses, or in QCD somewhere else. And in the standard model, there are both. So there is, that's why you see the Higgs web both here and in the QCD scale. And finally, you need the weak scale to be larger than the QCD scale. And okay, a priori, there is no reason for any one of these 3 things to be true, but they turn out to be true. Okay, so
where does that play a role, the last condition?
The last one, because let's say that the Higgs mass was much smaller, then when you close the instanton loop, so let me draw it on the blackboard, maybe it's easier.
It's here.
Well, essentially, when you close the instanton loop, the contribution that wins is not the web of the Higgs, but closing it at 2 loops.
Yes.
Yeah,
Okay.
so that's. Okay, so
By land QCD, you don't mean F5.
I mean,
Or you mean
the scale that dominates the instanton loop, so the one where the coupling is largest. So if I here,
in the cup.
oh, thanks. Yeah, so I'm just saying that so you can think of the instanton as some sort of effective vertex with all the fermion zero modes coming out, and then you want to close all the legs, so you do it with a Yukawa, and with Yukawas everywhere. And so now, okay, what I was saying before is that if the QCD web is much smaller than the QCD scale, this one dominates over the one where you put it to its web. And then this object, so when you close all the legs, is going to give you a contribution to the web of GG dual that goes roughly like this. Okay, there are many other factors, but these are the important ones. And so it's exponentially dominated by the scale where the coupling is large. And so you want this scale that I call lambda QCD to be smaller than the X web, otherwise you close this loop. So, okay, so I think I've given you enough philosophy for today. And now let me show you how in practice you can use this operator to explain theta and the X at the same time. So the idea is schematically the following. So you have to imagine that you have a multiverse, or at least a landscape. So somehow many values for the X mass squared and the theta angle are populated. And so I'm just going to have in the back of my mind the usual string theory multiverse, where you have a high energy theory with many vacua. In each vacuum, the parameters of your four-dimensional low energy theory can be different. And then inflation populates all these vacua. And so you end up with some universes where the X web and the theta angle are accidentally small just because they're tuned. And there are so many of these universes that there's going to be at least one or a few universes where these accidental cancellations have a probability of 1 to happen. And then, so the model essentially has a dynamics such that after reheating and after a time of order 10 to the minus 5 seconds, so when you get to the QCD phase transition, all the universes where the X web is too big or too small and the theta angle is too big crunch. So essentially, the cosmological constant becomes large and negative, they get a huge curvature and they become tiny. And the only universes that don't have this issue, so that where the cosmological constant remains whatever it is, are those where the X web is in a certain interval and the theta angle is bounded from above. And so these universes are the only one that expand and become even remotely similar to the one that we have today. So how do you do this? Well, so first of all, let me say that this crunching idea was already used by Cha, Baitai, Michael, and Tomer to explain the cosmological constant, and then we used it to explain the value of the X boson mass in very different way from what I'm going to tell you today. And before showing you how this crunching is implemented, maybe I should mention a few caveats on this whole picture. So up until a few years ago, this idea of a multiverse coming from string theory maybe was not loved by everyone, but was certainly considered consistent by everyone. Now there are some doubts. So many conjectures have been put forward on the behavior of string theory at low energies, both from the string theory side and from the more particle side, let's say. And so many people feel differently today about having eternal inflation or having de Sitter universes or even anti-de Sitter vacua that live forever. In practice, all I want to say is that all these issues kind of factorize compared to what I'm telling you today, because you don't really need eternal inflation to populate a multiverse of the size that we need. So you need maybe about 1,000 defaults. And there are examples of inflationary potentials that are consistent with all these conjectures. They're not incredibly beautiful, but we are working on it. So I think eventually we will be able to write a steep inflationary potential consistent with everything. And also, well, you should keep in mind that what I really need is a landscape, not a multiverse. And there are ways of realizing many different values of the X mass, for example, in ways that do not require a multiverse. So one example is the relaxation, where there is a scalar rolling down its potential and as the scalar rolls down, the X mass changes. Another example is a naturalness, where you have many copies of the standard model that all live in the same universe. But in any case, the short, the take-home message from this slide is just that these issues must be kept in mind, but they largely factorize compared to what I'm going to say today. Okay, so after this longish introduction, let me tell you how in practice the crunching is realized. So I'm going to add to the standard model two scalars that I'm going to call phi plus and phi minus, which are going to be very weakly coupled. For simplicity, I'm going to show you a model where these two scalars are also decoupled from each other, at least at free level, but it's not crucial, okay? It's just for making the presentation more streamlined. And the scalars are going to have their own potential and then a coupling to the X. The schematic idea is the following. So the scalar phi minus has a potential that on its own looks like this. So it has a shallow minimum and a deep minimum. So in this minimum, the cosmological constant is so large that no matter where you are in the multiverse, you have a negative cosmological constant. So if you find yourself in this minimum, the universe always crunches. If you turn on the X coupling to this phi minus and the X value is too big, it's going to destroy the shallow minimum. And so all universes where the X value is too big are destined to roll down and crunch. The scalar phi plus does the opposite for you. So left on its own, it wants to crunch. But if you turn on the coupling to the X and the X value is large enough and at the same time theta is small enough, then you generate a safe metastable minimum. And so the, let's say, key naturalness requirement of this model is that you have these two widely separated minima. One simple way to do this is if you just write down the most vanilla superpotential you can imagine for a chiral superfield, then you're going to get a potential with two minima that are degenerate, but they can be very far away from each other in field space. So you can dial these supersymmetric dimensionful parameters in such a way that these two minima are both at the same energy, but very far away in field space. And then if you add a small SUSY breaking term, this is going to split them. And even if the term is very small, so much smaller than the supersymmetric contribution to the potential, these two minima are far away, so they're going to be split by a large amount in energy. So this is, let's say, the most honest way in which one can stabilize this hierarchy.
Why do you need supersymmetry instead of simply copying?
You can also do it with approximate scale invariance if you want, but you need a symmetry that can stabilize hierarchies. So you want to make natural the fact that this potential has two very different scales built in, one associated to the shallow minimum and one associated to the deep minimum. So you're not really forced to use supersymmetry, but it's the easiest thing to do. But what I'm going to show you, well, it's if you want a toy model, which corresponds to zooming in into the shallow minimum, so no supersymmetry. And well, okay, you see it's a toy model because it has a negative quartic, so this potential on its own has a runaway direction, but it's very useful for presentational purposes, let's say. So I can also show you, if you want, at the end, a way to UV complete this potential using scale invariance and stabilizing the hierarchy between the minima. But for the moment, I will just show you how the mechanisms work, assuming that this is the potential. And so if this is the potential, it's going to look like this for the two scalars. So phi minus has a positive mass squared and a negative quartic, so it has a minimum at the origin and then this runaway direction. And phi plus has a negative mass squared and a negative quartic, so its potential just looks like this, with a local maximum at the origin. And these two scales that I call m minus and m plus, which are just the mass divided by the square root of the quartic, essentially give you the typical size of the potential, sorry, the typical field excursion over which the potential is constant in some sense. So in the case of phi minus, it gives you the distance between the two maxima. In the case of phi plus, it gives you the region where this potential is relatively flat. Okay, in addition to this toy potential, I'm also going to add this axion-like coupling to the operator that we've been talking about until now. And what I'm going to need for the mechanism to work is that these axion decay constants are much bigger than the scales of the potentials that I just defined for you. And here again, I'm doing something that can be justified with symmetries, because this scale associated to the potential I showed you on the previous slide and these axion decay constants break different symmetries. If you want, this idea is similar to what happens in QCD. So these axion decay constants, you can think of them as the pion decay constant, and the scale of the potential is not so dissimilar to the quark masses. So it's not so weird to have a hierarchy. But if you accept this hierarchy, then let me show you what happens. So what happens is that in a neighborhood of this local region of the phi potentials, so in a region of order m plus or m minus, you can expand the potential coming from QCD below the QCD phase transition. So as the universe cools down and the temperature goes down, this operator will eventually generate a potential for these two axions, which is going to be proportional to the QCD scale to the fork in that universe. So it's going to be a function of the xbev, and it's also going to depend on theta. Okay, and I'm taking these f's large enough that in a region of order m plus or m minus, I can keep just these leading terms of the potential for phi plus and just this leading term of the potential for phi minus. So let's see what happens to this model after the QCD phase transition. So initially, phi minus looks like this. So if you are an unlucky universe that started its life somewhere here or somewhere here, you're going to die anyway. If you're a lucky universe, you might find yourself in this minimum, which is a local minimum, but it's cosmologically long-lived. And then at the QCD phase transition, this part of the potential turns on. So you get a tadpole for phi minus proportional to the xbev. If the xbev is too big, this tadpole is going to destroy the local minimum and it's going to kill you, even if you started off as a lucky universe. For phi plus, the situation is the opposite. So again, if you start your life here or here, you're dead anyway. But if you start your life up here, and you imagine that the phi plus mass is smaller than Hubble at the QCD phase transition, so it's 10 to the minus 11 eV or so, then you're going to be stuck until then. And so you have a chance to survive. Because at that point, this other part of the potential turns on, and you see you get a positive mass for a plus, and also a tadpole. This means that if the tadpole is small enough, this positive mass is going to win here, potentially, if the xbev is large enough, and generate a minimum. Okay, but for the minimum to exist, you need two conditions to be true. First of all, you need the xbev to be big enough, because you want this mass, positive mass, to win over the negative mass. And secondly, you also need theta to be small enough, because this theta essentially is shifting the place where the positive mass starts becoming important. And so if you shift it too much to the right or to the left, then this mass can never generate a minimum because it's competing with a negative quartic. So the dynamics might seem a little bit involved, and it is, but the model is extremely simple. So literally, I'm writing down the simplest phi square phi to the 4 potential I can imagine for two scalars, and then I'm giving it a coupling to the gluons. And this simple theory solves in one go, so it explains to you in one go why the X mass is small and why the theta angle is small. So notice that you could have started with any theta angle in this theory, but if theta was large, you would never have generated a minimum for phi plus. Yes, so maybe before going to the phenomenology, let me mention also what I consider the drawbacks of this idea. So if you look at it from low energy, it looks very clean and simple and nice. But of course, we're making some strong assumptions on what happens at high energies. Because here I'm telling you that these two scalars, phi plus and phi minus, are those that have the deepest minima in all the landscape. And these two scalars are also those that couple to the X in this way. So maybe this will require some complex model building in the UV. So when you're able to write all your string theory vacua, maybe it will be non-trivial at all to generate a theory like this, but given our current knowledge, it's hard to tell. So this, if you want, it's like my full disclosure. So what I like the least about the model. Yes.
Yeah, I'm a bit. I just want to know your opinion. So it seems like most of the universe are just the wrong universes because they crunch.
Yes.
So it's like it's the wrong prediction.
What do you mean? So you need a big landscape because it's not enough to have the right X7 and the right theta angle to survive. You also have to start your life close to the local minimum. Yeah, but again, this is a question. So how many universes you need is a question that for now we cannot answer because we don't know the measure in the multiverse. We know nothing. I mean, maybe all universes start their life here for some reason, but we don't know.
So you have to advocate something as the anthropic principle to say I am in the right.
Yes, so in a sense, this is an anthropic solution, but it's using the same anthropic principle as the cosmological constant, because so these universes that I say die or crunch essentially become very small and have a huge cosmological constant. And for the usual argument by Weinberg, we think that those cannot oft observe. Right? Maybe actually, I don't even care too much if they do oft observers that maybe live on very short time scales and they're tiny, so they're, I don't know, size 1/n Planck, they live for a time 1/n Planck. That's fine, actually, because what I'm saying here is that the only way to have a universe that looks like our own, that's macroscopic and is in agreement with the observations that we have, is if the X-Bev and the theta angle appear unnaturally tuned. So essentially, I'm relating to you the size of the universe with these two parameters. So yeah, in a sense, it is anthropic because it's essentially relating the CC and the X and the theta angle, and then leveraging the power of the anthropic power of the CC. But it's very different from what you would call anthropic for the X and all these details with the atomic principle, etc., etc. The scalars in principle can also be dark matter. Actually, phi plus, given the hierarchy of decay constant I've chosen, typically it's the dominant component. Interestingly, because I assume that the size, let's say, of the characteristic size of the potential is much smaller than F, then the prediction for the relic density is different compared to the normal prediction for axions. So these objects can be dark matter in the same way as the axions. So for instance, produced via misalignment, but they can be misaligned from their minimum much less than the axion. And parametrically, what you find is that the relic density is suppressed by theta squared compared to the axion, which means that you get the right amount of dark matter only if the mass is very small. And interestingly, since theta today is related to how far these scalars are from their minimum, and also how much dark matter you have today is related to how far these scalars are from their minimum, you can draw a line. So if this phi plus is dark matter, and you measure the mass of dark matter, you predict theta, and vice versa. So this is, I think, quite cute. I mean, I've never seen a signature like this before. And even more interesting, you can kind of close the whole parameter space between fuzzy dark matter observations and neutron EDM measurements. Of course, phi plus doesn't need to be dark matter, but if it is, there is this signatures that are quite special to the model. So you either see a neutron electric dipole moment and then predict a dark matter mass, or vice versa. I'm not honestly sure which ones of these experiments are going to get there first. I know that the time scale for the neutron EDMs is of order 5-10 years. Okay, so having said this, I'm done with the main part of the talk. since there is some more time, I will tell you a few things that are more general than the model I presented. So first of all, I should say that in addition to this model, there are a few other ideas to explain mostly the value of the Higgs boson mass cosmologically. So they're not all similar to the one I described, but the underlying principle is similar. So there is some event in the history of the universe that selected the Higgs boson mass that we see today. And if you look at all these papers, they all look very different from each other. They don't seem to have much in common, but the vast majority of them shares this structure. So we are all secretly outsourcing the hierarchy problem to a sector where there is a symmetry, either supersymmetry or scale invariance, but one of the symmetries we know that can protect a big hierarchy of scales. And then we couple this sector to the standard model very weakly in such a way that this hierarchy is preserved. And this coupling to the standard model selects the Higgs mass out of a landscape. And I like to show this slide because it shows you that even if the logic might appear completely different from traditional solutions to the hierarchy problem, where you have supersymmetry at some scale or you have composite peaks at some scale, in reality, they are secretly very similar. So what's really solving the problem, it's again one of these symmetries. We're just hiding it from sight. So before moving on to some general features of this model of cosmological selections for the Higgs mass, well, I just summarized the qualities of the model that I just described to you. So I already told you what I consider the biggest flaw. But if you accept that these deep minima for the scalars exist, you're getting a lot in return. So you are explaining at the same time the value of the Higgs mass and the theta angle with a very simple model, adding just 2 degrees of freedom to the standard model. You're not doing any violence to inflation. I'm saying this because many of these ideas that select the Higgs mass cosmologically have strong requirements on the inflationary sector. You can, in principle, have the cutoff of the Higgs mass be anything, including M Planck. Unlike, well, some anthropic solutions, well, not really some, but some let's say statistical solutions that try to argue that the patches with our Higgs web are the most likely. This has no problem of measure because independently of the measure, you're just crunching away all the universes that you don't want. Finally, well, this model is much simpler to UV complete than the relaxation because, well, so a potential obstacle to UV completing is that you have both an axion-like coupling and a non-compact potential. And for the relaxation, this is potentially a big problem because you see many oscillations over the scale of the non-compact potential. So somehow you have to explain how a field that can look both periodic and non-periodic, how it can be an angle but also not be an angle. Instead, here you don't see any wiggles. So essentially, you're just using some general decoupling arguments, right? So a periodic field can look non-periodic if you zoom in on a field range that's much smaller than its period. So in practice, there are many known ways to UV complete this model. It's, for example, using axion monodromy, while there are not so many known ways to UV complete the relaxation, as far as I know. And finally, well, if the scalars are dark matter, there is also this very interesting correlation between the neutron EDM and the dark matter mass, which I'm not aware exists in any other model. Okay, so since I guess I still have a few more minutes, I'm going to tell you something related but different. So even if you don't buy all this cosmological selection story, you don't like the multiverse, you think that the scalars will never be UV completed in a reasonable way, I think you should still take home the message that there is essentially only one local quantity in the standard model that depends on two parameters that appear incredibly tuned. So I think that this lesson, even if it was known by 50 years, it was not appreciated enough. And so even if you hated every single slide of this talk, I think you should still go home with this message, which is just a simple fact about the standard model. And this simple fact, it's interesting also for another reason, because so you can start asking this question beyond the standard model. And the reason why you want to ask this question beyond the standard model, well, it's twofold. First of all, if you find operators like this one, you can use them to solve the hierarchy problem in many different ways. So in some sense, this is kind of the phenomenological cornerstone of this class of ideas, because even if you don't like a particular model, it will still need some operator that is sensitive to the X-Web. And so if you find an operator that is sensitive to the X-Web, you actually discovered something that is in general relevant to the problem of the X-mass. And when I say sensitive to the X-Web, I really mean this. So I mean that if you change the X-Web at order 1, your quantity also changes at order 1. Because of course, otherwise everything depends on the X-Web, but by a tiny fractional amount. But this is useless to explain the value of the X-Web for reasons that if you want, I can explain, but it should be clear from the potential I showed you. So if you change the web by order 1 and your potential is changing by 10 to the minus 34, you need a tuned model that is sensitive to changes of order 10 to the minus 34 to do anything. So, okay, so the condition that we really are interested in is this one. And I've already told you what's the answer in the standard model, but, well, you might want to try to go beyond. And it's not so easy because in practice, you're going to need new physics that is lighter than the weak scale. Otherwise, you will reintroduce the hierarchy problem. So otherwise, these quantities will never depend at order 1 on the X, but will depend on some bigger mass scale. However, well, if you can find these quantities, it's very rewarding for two reasons. One that I've already said, so one of these trigger operators, like I'm going to call you, potentially corresponds to many solutions to the hierarchy problem. So you found something relevant phenomenologically. And secondly, because of this condition, you also found something that is within reach, maybe actually, well, of the ILUMI LHC or future colliders. And so, well, okay, this is just a list of all these cosmological ideas. Most of them rely on these trigger operators. So what could be some potential candidates? So in the standard model, you can try, for example, the same object that you constructed for the gluons, but for SU2. Well, the difference here is that the symmetry that is anomalous under SU2 left is B plus L, as you know. And so technically, purely within the standard model, if you couple something to this operator, it's unobservable. You can rotate it away. You can add extra B plus L breaking beyond the standard model, but it has to be a special B plus L breaking. So if you just add neutrino masses, it's not going to interfere with the SU2 instanton. You need an operator that can close all the legs of this instanton. And it turns out that it's not so easy to make this object observable without incurring into bounds that already exist. We're now working on it. So we don't know yet what the answer will be, but I suspect that the final answer will be that it's hard to find, I mean, we will not find something viable phenomenologically. Another option is to write down operators that are protected by approximate symmetries. So, for example, flavor symmetries in the standard model. This is fine if you are interested in explaining the value of the X mass up to some scale, because these operators will become sensitive to high energy scales at high loop order. So this one, for example, at 3 loops. So if your cutoff is a few tenths of TeV, this object could still depend at order 1 on the X mass squared. So its vacuum expectation value could still be sensitive at order 1 to the X mass squared. But if you want to explain why the X mass is not much smaller than M Planck instead of 10 TeV, then these operators are useless for the reason I said before, because as you change the X-Web, their web will change only by a tiny fractional amount. However, if you add new particles, then there is a simple, there are at least 2 simple options, but I do not know more than 2 simple options. One is if you add a second X doublet, and then this operator could do the trick. So if you add, if you make it odd under some Z2 symmetry, then its web is calculable in the infrared and depends only on the X web, essentially. what makes this interesting but also challenging is that if you impose that Z2 symmetry, essentially all dimensional full parameters in your 2HDM, so B mu, except for the masses, are set to 0. Also, these other quartics are set to 0. So you're left with this potential. And if you ask what's the spectrum of this theory, well, you'll find that the charge and pseudoscalar X's are at most a few hundred of GeV, because, as I said, the only mass scale are the masses. So the only mass scale in this theory is the weak scale. And so the masses of these objects are a coupling times V squared. And if you make this coupling much larger than 2, then you hit a Landau pole almost immediately. And the mass of the CP X is actually smaller than the one that the X that we observed. And so, okay, a priori you might think that this is already excluded, and it almost is, but we did our homework in this paper. We call this the type 0 to HDM for fun, well, because it's kind of a type 1 from the point of view of Yukawas, but we're setting to 0 all these parameters. And then, well, so if you choose these Yukawas, which correspond to a certain choice of charges of the port bilinears under this Z2 symmetry, then the model is not already completely dead, but almost. So here, okay, you can see why it's hard to keep it alive, because going from left to right, I'm increasing the web of the new doublet compared to the weak scale. And so going from left to right, the indirect constraints become more and more important. So you see that, for example, B2S gamma here, it's almost completely excluding everything, while here it's not very important. However, if you push in the opposite direction, so if you make the web small, then you're also making this new CP even X light. And so then direct searches become more important, or you start eating Landau poles if you want to make it heavier. And so in practice, you cannot decouple this model, and you get a target for high luminosity and FCC. You see, I mean, in this way of showing things, so the mass of the charge X versus the mass of the CP X, there are only small regions that are still alive. Here, maybe the colors are not very clear, but there is this region and this region. If you take a more detailed look, you'll find other regions, but in practice, as you can see from these purple dashed lines that I'm not gonna tell you too much about unless you ask, ILUMI LHC or FCC E plus E minus can cover all these regions. And actually, these regions, even if they're alive, they're even a bit tuned. So they're tuned at 10%. So from this exercise, you see how hard it is to find operators that are sensitive to the X-web, even if you allow yourself infinite pressure. The only other example that I know is adding a new gauge group and using the same as GG dual, but for this new gauge group. However, also here, you're going to have new physics that it's light, because to make the potential coming from this operator or the web of this operator sensitive to the X-web, just like in QCD, you need either to have the masses of some particle charge under this gauge group depend on the X-web, or to change its running depending on the X-web. And in practice, so the only model I know that works is by adding vector-like leptons that have an order 1 fraction of their mass coming from the X. And so this is also something that you can see at ILUMI LHC or FCC EE. So to conclude the second part of the talk, the take-home message is that these trigger operators are interesting, because to each one of them you can associate many solutions to the hierarchy problem. And even if you don't like these cosmological explanations for the X-web, still you're kind of asking a general question. So are there local quantities that depend on the X-web? So this might be just related to the problem in new ways that we've not even thought about. And so this is the interesting message theoretically, but then there is also an interesting message phenomenologically, which is that you always need, if you want to go beyond the standard model, to add new physics that is lighter than the weak scale. So these are perfect targets for what we're doing now. And essentially, if you want, they're giving us completely different targets that are related to naturalness and might tell us something important about nature. Plus, we have only essentially these 3 targets. It's not that we have an infinite collection of them available. As far as I know, these are the 3 ones. So this one in the standard model and this two in BSM. Of course, this is not a theorem, so if you're interested in finding new ones, you're more than welcome, but it's not easy at all, as I've shown you very quickly in the last couple of slides. Thank you very much.
Thank you very much, Raffaele. Are there any questions? Yeah.
Yeah, in the first part of your talk, you didn't introduce a coupling among the square of the pi plus and pi minus.
Yeah.
How important was that for the results that you got?
Yeah, so if you keep it of the same order as the diagonal quartic, then it doesn't change the story. So yeah. So, but if you make it much bigger, then it does. But then, okay, if you make it much bigger, it's not even natural. Then you create instabilities in the potential. So, so if you do the most reasonable thing consistent with symmetries, it's still okay. So I didn't do it because it's much easier to visualize it this way. But,
So
yes.
maybe it's naive. When you said, like, in the possible evolution of the crunching universe, you have to be lucky when you have to start at least there. Right? If you assume inflation for the scalar speed, you will be displaced and possibly end up in where you don't want to.
Indeed, that's true. So, okay, there are two options. Either, so I didn't really tell you explicitly what these scales are, but in principle, they can also be very large. Okay, you can say this F is M Planck, this M is 10 to the 10 GeV. And then I could just say that the scale of inflation is small enough that it's not, if I start my life here, it cannot move me all the way beyond the maximum. The other option is that you just accept that you need to be even more lucky, right? Because inflation will essentially give you a random walk with steps of order Hubble. And so even if Hubble is bigger than say the scale, some even luckier universes will have a random walk that in the end still keeps you within this range. So you make a step in this way and a step in this other way and so on. So this second option, of course, needs you to be exponentially lucky. But the first option instead is much simpler.
Which is good to, yeah, sort of, to consider this effect, you have to impose somehow that these F plus and minus are above a certain scale. So
yeah, actually, I think it, so we essentially in this paper, we outlined the idea, but I think it might be interesting to be more explicit and say, okay, if I want a reasonable inflationary sector, these are the bounds on F plus, M plus, etc., etc. But, well, what I can tell you is that, well, here, F plus and M plus are huge. Actually, this plot is not so friendly with all the swamplandology that I was talking about before, because the mass of this pi plus essentially is the same as the axiom. So it's lambda QCD squared over F. So to get these values, you need F to be super Planckian. And so in that case, yeah, okay. The answer to your question is it's very easy. Hubble is smaller than M, but you are making Vafa unhappy. Yes.
So you have ignored the measure problem in a way.
In some sense, but
As you said, it's just enough if some fraction of the universe has the property that I want.
yeah.
But still, if I look at the potential, please visually, it looks very unlikely, also, or very unlikely, sorry, to be precisely what you want, right? At least it is runaway behavior that you're showing. So, isn't there some sort of problem?
Well, I mean, essentially, you just need the multiverse to be big enough. So to make by unlikely you mean that the scale is much smaller than the rest of the field excursion. This is true. So even if you be complete it, I want this part of the field dispersion to be bigger than this part. I mean, not enormously bigger, but bigger. Yeah, I mean, the answer to that is that, so I would not say that it's the same as a measure problem. I just would say that you need a much bigger multiverse than you normally need. So you don't just need to scan the X mass or the theta angle, but you also need, say, to scan the position of this phi now. But again, these questions, until we are able to actually write a model of the multiverse, are a bit philosophical in the sense that maybe I will be able to write a model that forces the scalar to always be in this region for some reason. So maybe at the price of model building, I make it much more likely. Yeah, those are all questions that we all would love to answer, but we cannot yet answer. But yeah, but indeed, so it's true that that this poses extra requirements on the multiverse compared, say, to just doing it anthropically in the vanilla way.
Okay. Are there any more questions? I don't see any, so let's thank Raffaele again.